طيب let's continue شباب our talk. Last time we consider the application of the first law of thermodynamics for a closed system. So now we have applied for the case of open system, like when we have an internal combustion engine or gas turbine. This is a kind of open system. So in this case, we can apply the first law of thermodynamics and we can calculate the power output. We have considered this example last time. As you can see, we have this is a gas turbine شباب used in power plant, in combined cycle power plant. Combined cycle power plant in which we have a steam turbine and the gas turbine as well. That's why we call it combined cycle. This is an already gas turbine that is in service. We have already provided the data, and then we can apply the first law of thermodynamics. This gas turbine is fed by natural gas, which is almost methane. We have written down the combustion equation, and based on that, we were able to calculate the power output. The power output of this gas turbine, which can provide power output of about 6 megawatt in this case. So this is the benefit of the first law analysis of a reacting system, that we can apply the first law of thermodynamics, and then we can calculate the power output of a given system. Either it is open system like gas turbine or internal combustion engine, or in the case if we have constant volume combustion or closed system, if we have explosion in a closed vessel, or if we have constant volume combustion like the case of gasoline engine, we have the combustion in gasoline engine is an instantaneous combustion, which actually just happen at the moment when we have a spark inside the cylinder. Then at this moment, instantaneously, actually, we get the combustion of gasoline. We consider it constant volume combustion in this case. And also we have learned how to apply the first law of thermodynamics. The main difference in case of open system, it will be Q minus work equal to the difference in enthalpy between product and reactant. And the case of closed system or constant volume combustion, it will be Q minus work will equal to the difference in the internal energy of product minus the internal energy of the reactant. Also, last time we talked how to calculate the heating value. We said for any fuel, we come up actually with this fuel and burn it with a stoichiometric air. Lambda is equal to 1. And then we cool down the combustion product until we get the same temperature, which is 25 degrees C. And almost this test is being done under atmospheric pressure. Then we absorb the heat from this combustion process. This heat actually should be representing the heating value in this case. And we said we have higher heating value and lower heating value depending on the state of water in the exhaust. If it is liquid, that means we have the higher heating value. We have obtained all of the heat of the fuel. If it is in the vapor form, that means this water vapor just have still actually part of the heat of the heating value. That's why we call it the lower heating value. Is it clear شباب up to this moment? طيب. Let's consider شباب today. We'll be talking inshallah today about the adiabatic flame temperature or the maximum temperature of a reactor, or adiabatic flame temperature of a combustor in any combustion system. So if we are considering, if we have, let's say we have a combustion system or any combustor in general, this combustor for any application actually, let's say for internal combustion engine or gas turbine or whatever, in all of these cases, we consider this combustion process as constant pressure combustion process. So for the first case, if we have constant pressure combustion, if the pressure is constant, how we can calculate the adiabatic flame temperature or the maximum temperature of this combustion process? Usually constant pressure combustion has some example, like the case actually when we have a diesel engine. The combustion in diesel engine is almost under constant pressure. After we inject the fuel, then it will take some time while the piston is moving until actually it mixes with the air, then it self-ignite, and then we can have the combustion. So usually the combustion process in diesel engine, it occurs actually while the piston movement. And in this case, we can consider in this case the pressure as constant. And this is unlike the case of gasoline engine. Usually gasoline engine, we have instantaneous combustion. So once we have a spark, we have this combustion at actually a given location of the piston. So usually it occurs at constant volume in case in case of gasoline engine. But in case of diesel engine, as we said, the fuel just needs some time and the piston will be moving, and in this case, we can consider the pressure inside the cylinder is constant. Also, another application in case when we have a gas turbine, usually the design of the gas turbine combustor is designed to have fixed pressure drop, fixed small pressure drop, and usually we can consider the combustion in the gas turbine combustor. Also, we can consider it under constant pressure process. So as an example for constant pressure combustion, we have the diesel engine, and also we have the combustion in the combustor of a gas turbine. Type, let's say we have a diesel engine or we have a gas turbine and we have a combustor, so it is fed actually plus of fuel plus air. This fuel plus air is being burned inside this combustion chamber, okay? And in this case, we should have the combustion product should be actually at high temperature in this case. But usually, Shabab, in case of diesel engine or gas turbine, usually some heat is lost from the system. Okay? Type, if some heat actually is lost from the system, that means the temperature actually of the product will be a little bit reduced in this case. Type, if we are able to design this combustor to have it adiabatic or fully insulated, this means actually in this case the heat transfer will equal to 0, and in this case we call it actually as a adiabatic combustion process. So the walls of the combustor are insulated, so we don't have any kind of heat transfer. That means, Shabab, all of the heat of combustion generated due to combustion will appear actually as temperature rise of the product. And in this case, the temperature of the product, we call it actually the adiabatic flame temperature. And in this case, this temperature, Shabab, is the maximum temperature of this combustion, depending on actually the fuel coming in and depending on actually the concentration of the oxidizer mixture. Because if we vary, let's say lambda or the excess factor of the air, if it is increased, that means actually part of this air will be used in the combustion, and the remaining part will act as a diluent inside the combustion chamber. And this diluent will reduce the temperature in this case. And even if the combustor is adiabatic, but in this case the adiabatic flame temperature will be less than the case if actually this lambda is equal to 1 or stoichiometric. So usually at a stoichiometric combustion, we can get the maximum adiabatic flame temperature, okay? But this adiabatic flame temperature will be reduced actually if this excess air factor is much greater than 1 or much less than 1. If also lambda is less than 1, that means we have incomplete combustion. You can see here, Shabab, here are the factors affecting the adiabatic flame temperature. You can see, first of all, using the air of combustion process. If we have excess air, that means actually in this case we have more air that will cool down the combustion product, so the adiabatic flame temperature will be reduced. And you can see here, Shabab, at equivalence ratio equal to 1. Usually all of the fuel, all types of the fuel have maximum adiabatic flame temperature under stoichiometric combustion or theoretical combustion. When we increase the amount, when we actually lambda equivalence ratio is less than 1, that means lambda is more than 1. So we have lean combustion. Lean combustion, that means the adiabatic flame temperature will be reduced in this case. And also in case, Shabab, if phi is greater than 1, that means lambda is less than 1, then we have incomplete combustion. So part of the fuel is not burned in this case. And in this case also that will lower the adiabatic flame temperature. You can see here, Shabab, this is the adiabatic flame temperature for different fuel. For methane, and the adiabatic flame temperature for propane is higher than that of propane at the same equivalence ratio. Also we have the adiabatic flame temperature of ethylene. Hydrogen have high adiabatic flame temperature, very close to the value of CO under stoichiometric combustion. And as you can see, for acetylene, it has actually higher adiabatic flame temperature. And that's why, Shabab, acetylene is used actually in the welding process, because it results in a very high adiabatic flame temperature in this case. So the factors that can affect, Shabab, the adiabatic flame temperature is the excess air. If I have more air or less air, that should affect the adiabatic flame temperature. Incompleteness of combustion. If we have less amount of air, combustion will not be complete and will not have the full heat release. Also, we have dissociation of combustion product. Usually some combustion product like carbon dioxide and nitrogen, at high temperature, they just dissociate. As I told you before, this nitrogen is converted to N plus N, and it recombines actually with oxygen molecule O2 or the oxygen radicals, and at the end actually it creates NO and NO2. And at the beginning, part of this N, not all of N will be converted to NO and NO2. Also like this, the CO2, carbon dioxide, will be converted to carbon monoxide plus O2. That means we have converted back the product into reactant. CO يا شباب is fuel. It has to be burning. So if we have dissociation and this CO converted back to fuel, this is a kind of endothermic reaction. It needs the heat. So it will take part of the heat here. And it will lower the adiabatic flame temperature. So if we have dissociation, that means we convert back the product into the fuel back, and that means actually it will absorb the heat and it will lower the adiabatic flame temperature. Yes, I think Ali, do you have a question? Ali? Do you have a question, Ali? Or yeah, Mustafa? Go ahead.
Yes. What about if we use pure oxygen instead of air?
Yes, pure oxygen in this case, it will actually highly, in this case, increase the adiabatic flame temperature. And this is yani in, as I told you here, if you can see, acetylene is used because it is in the welding process in order to weld the material, melt the material so that they can be welded. So we need high temperature. Acetylene can result in higher adiabatic flame temperature. If you are not using air, if you are using pure oxygen in this case, the idea شباب of pure oxygen, air itself has oxygen also, but there is actually some N2, 79% N2, and this N2 acts as a diluent. It just absorbs a part of this heat. But now if you are just using oxygen, so we don't have any diluent in this case. So actually the temperature in this case will just raise, it can approach actually 3000 degrees C in this case. In case of acetylene oxy combustion, it can approach this way. Okay, but in case of air combustion, usually the adiabatic flame temperature is around 2000, 2200, something like this. But with pure oxygen, it can exceed 3000 degrees. Okay, so this is يعني شباب the case. طيب, if we have a adiabatic combustor here, we said the temperature of the product will be the maximum temperature. In this case, we call it the adiabatic flame temperature. Now in this case, شباب, we are talking about the combustor. We are not talking about the whole engine. So we don't have work in this case. So just we are considering the combustor. We have reactant and the product. Apply the first law of thermodynamics, Q minus work equal to enthalpy of product minus the enthalpy of the reactant. We don't have work. The system is adiabatic. That means the condition for adiabatic flame temperature is at when we have actually the enthalpy of product is the same as the enthalpy of the reactant. But usually, شباب, in order to calculate the enthalpy of product, in this case, we have to have the temperature of the product. Then we can calculate delta H. Enthalpy of the gases of the product is enthalpy of formation plus delta H. So I need this temperature to go to the table and then get delta H. But actually, in this case, we need to calculate this temperature. That means in this case, this should be done actually by trial and error. So the solution here will be done actually by trial and error in this case, as we can see, inshallah, right now. So this is the first case, شباب, when we have constant pressure combustion. And an example for constant pressure combustion is the case of combustion in diesel engine, in which the combustion takes place while the piston movement. We can consider it in this case as constant pressure combustion. Inshallah, we'll be talking about the cycle of the diesel and the gasoline engine, Otto cycle, diesel cycle, dual cycle. Inshallah, we'll be talking about all of them in the next chapter. Next week, inshallah, we'll start with the engine cycle, and you will see for the case of diesel engine, in the diesel cycle, the combustion takes place at constant temperature. So if I told you in the exam I have a diesel engine combustion and they calculate me the adiabatic flame temperature, so you will follow the analysis of constant pressure combustion, H product will equal to H reactant. For the second case, if we have constant volume combustion. Constant volume combustion, I told you, there is the example for this actually is the gasoline engine. When we have a gasoline engine, a spark plug initiates the combustion inside the cylinder, and then instantaneously at the same moment we have the combustion is done, so we consider it constant volume. Inshallah, we'll see the cycle of gasoline engine, which is the Otto cycle, and you will see in this case that the combustion takes place in the gasoline engine. In the ideal cycle of gasoline engine, it takes place at constant volume in this case, or the volume actually, while the combustion process is constant in this case. And also, شباب, if we have an explosion in a tank, in a fuel tank or something, so this is a closed tank. We call it rigid tank, or we call it actually rigid vessel. All of this actually, this is a closed system of constant volume. So if I told you I have rigid tank, rigid volume, closed system of constant volume, we have gasoline engine or a spark ignition engine. In this case, actually, that means actually the combustion in this case under constant volume. Type if the combustor, the same. We have the combustor also is adiabatic. So the heat transfer is equal to 0. And here we have the reactant, fuel plus air, and we have the product in this case. In this case, if the combustor is adiabatic, that means in this case we are talking about the combustor, so we don't have water. So that means the temperature of the product should equal to the adiabatic flame temperature or the maximum temperature in this case. But in case of constant volume combustion, if you apply the first law of thermodynamics, it will be, as we have proved last class, that should equal to the difference in internal energy of the product, U product, minus the internal energy of the reactant. Here we don't have heat, it's adiabatic, we don't have water. That means the condition in this case for the adiabatic flame temperature is the internal energy of the product should equal to the internal energy of the reactant. And we have defined the internal energy of product or reactant as summation of number of mole for each component in the product or in the reactant multiplied by H, which is in solvent formation plus delta H, minus R universal or R bar multiplied by temperature, like what we have done last time. So it is the same. Delta U is the same as delta H, solvent formation plus delta H, minus the universal gas constant multiplied by the temperature T. And that's the conditions that we apply in order to calculate the maximum temperature. As I told you, we don't have the temperature of the product, so I will not be able to calculate U product. Delta H for the product I cannot calculate unless I have the temperature. And that's why I will just play trial and error by this condition until I get the temperature of the product in this case. Okay? Is that clear, Shabab? Is it clear? If I have a constant volume combustion system and a constant pressure combustion system with the same fuel, same combustor, but we just change from constant volume to constant temperature. The adiabatic flame temperature at constant volume will be greater than or less than the adiabatic flame temperature at constant temperature. Which one will be greater? At what?
Constant pressure will be higher.
Will be higher?
I think.
What do you see, Shubha?
I think the constant volume will be higher because all the product energy is converted to the heat.
Exactly, in this case, Shubha. So in case of constant pressure combustion, Shubha, we said example is the diesel engine. So we have this is the engine, and we said in case of diesel engine, this is the injector that injects the fuel. But it injects the fuel and it takes time. So while this time the piston is moving. Okay, so in this case, if we have in this case the input heat of combustion, this heat here, okay, when we have the combustion take place, this heat actually will result in the adiabatic flame temperature. It will raise the temperature actually of the reacting mixture in this case. But actually part of this heat in case of diesel engine, in order actually to keep the pressure constant, in case of diesel engine, this piston has to be moving. And usually, the combustion takes place during the expansion stroke, when the piston actually is just moving down. So to keep the pressure constant, because the only way for a closed system, in order to keep the pressure constant, is through the movement of the boundary, one of the boundary here, actually, if we are talking about this system, is the piston. And in order to have constant pressure combustion, this piston actually has to be moving in order to keep the pressure constant. Because when you add heat, in this case, heat will raise the pressure, will raise the temperature. But actually, in order to keep the pressure constant, this piston has to be moving down in this case to have constant pressure combustion. But this piston, in order to move down, it will take actually part of this heat. It will consume part of the heat generated due to combustion. That means actually in this case the adiabatic flame temperature will be less in case actually if we have constant pressure combustion compared to the case of constant volume in gasoline engine. In constant, the piston is not moving. It's an instantaneous combustion. At the same moment we have a spark plug, the spark is initiated, then we have the combustion at constant volume, the piston is not moving. So we don't have work consumed to move the piston. So that means all of the heat of combustion will appear actually in terms of adiabatic flame temperature in this case. Okay, so let's solve this example and see how we can calculate the adiabatic flame temperature. But you have to look at the system, Shabab. First, is it constant temperature, open system, constant pressure applied for the open system, or it is actually constant volume applied to the case of gasoline engine, or when we have a rigid tank or closed volume, closed system of constant volume combustion. Type here he said butane. Butane, which is C4H10 at 25 degrees C, is mixed with 150 theoretical air, so lambda is equal to 1.5. This air is coming at 600 Kelvin, is burned in an adiabatic combustor. So what does it mean, adiabatic, Shabab? So the heat transfer is equal to 0. And we are talking here about the combustor. We are not talking about the engine. Okay? So combustor, and this combustor is adiabatic. That means actually the temperature of the product is equal to the adiabatic flame temperature in this case, for the maximum temperature. Okay? We consider a steady flow combustor, so that means this is an open system, constant temperature. With the temperature of the product, what is the temperature of the product actually during out of this combustor? Okay, so this is the combustor. We have fuel is coming in. This fuel is C4H10, which is butane, coming at 25 degrees C, is burned with air with 150 theoretical air, so lambda is equal to 1.5. This air is coming at 600 Kelvin. We have to know the temperature of all components, and then this combustor is adiabatic, and by default this is a combustor. We don't have work, it is not connected actually to an engine. Then we have the combustion product. Those combustion products should be at the maximum temperature or adiabatic flame temperature, which we need to calculate. Type the first step, I will just write down the combustion equation. So C4H10, we have 1 kilomole plus lambda, which is 1.5, gamma, which is x plus y over 4, or m plus n over 4. N over 4, that should be 6.5 O2 plus 3.76 N2. And that should give us 4 CO2 for complete combustion, 5 H2O, lambda minus 1, which is 0.5 by 6.5 O2, plus lambda, gamma, 3.76 N2. And those are the product in this case. This fuel is coming at 25 degrees C. This air is coming at 600 Kelvin. Okay. But actually those products at the adiabatic flame temperature, which we don't know in this case. Apply the first law of thermodynamics. We will say H product is equal to H reactant. Okay, and then Salby of reactant. We have already the temperature of the reactor, so we can calculate the enthalpy of the reactor. We have 4. We have 1. Enthalpy of formation plus delta H for the fuel C4H10. This fuel, Shabab, he said gaseous fuel, because the enthalpy of formation, as you know, will be different. You will just go to table A4, you can just get this value enthalpy of formation for butane. But it is coming, Shabab, at temperature 25 degrees C. That means delta H in this case should be what? 0 for the fuel. Okay, plus we have oxygen. Oxygen and nitrogen are natural compounds, so in this case their enthalpy of formation is 0. So we have delta H, but they are coming at 600 Kelvin. That means we have delta H in this case. So it will be plus 6.5 delta H of O2 plus 6.5, 1.5 multiplied by 6.5 plus 1.5 multiplied by 6.5 multiplied by 3.76 delta H of nitrogen. Those values, شباب, of delta H for the O2 and the nitrogen, we can just go to table A3. I can get those values in this case. طيب, if I substitute, I will find in this case, شباب, that the enthalpy of the reactant will equal to this number. So let's write it down. So from this reaction, based on the temperature of the reactant, I can calculate H reactant in this case. So if you calculate H reactant, the enthalpy of the reactant, it will equal to 289952 kilojoule per kilomole fuel. Okay, so that is the number in this case of H reactant. And H reactant, because of fuel and the exothermic reaction, usually it will be a positive value. Okay. Then what about H product? H product will equal to the product are 4 CO2, so 4 enthalpy formation plus delta H for CO2 plus 5 the same enthalpy formation plus delta H H2O plus 0.5 by 6.5 delta H for O2. So شباب, O2 and N2 are natural compounds, so don't have enthalpy formation. So just forget about it. Plus 1.5, 6.5, 3.76 delta H for N2. Okay, but to get delta H, this I need the temperature. This delta H of the product. For the enthalpy formation for carbon dioxide, I can get this value from table A3. The enthalpy formation of water vapor, I can get it from table A3 at the top of the table. I don't need the temperature. But now I don't have the value of delta H to calculate H product. So what should I do in this case? I will be assuming that the temperature of T product, let's at adiabatic flame temperature, the temperature should be around 2000. يعني, okay? So let's assume the temperature starts from 1500 degrees. Okay? I'm assuming this. So assume T product is equal to this value, or adiabatic flame temperature. Yeah. Then I will go to H product and calculate H product. Now I have the temperature. This H product should equal to what? The enthalpy of the reactant. But usually you will not find it. You cannot just get it actually from the initial shock. So in this case, you will get this value for H product. Then I will calculate the difference. H product minus H reactant. This difference, شباب, at the adiabatic flame temperature, H product should equal to H reactant. So that difference should equal to 0. But with this assumption, this temperature is not the adiabatic flame temperature. So we should have some difference here. Okay? Let's say this difference, if you assume the temperature is 1500, you will find H product is equal to a negative value. So that means it is less than this value. This value, شباب, is a positive value. When I calculate H product and I found it negative value, that means still H product, I don't know how to do. So H product, this is the product, is less than H reactant. So I have to make another assumption to get H product higher than H reactant. Then I can interpolate, okay, to get actually the condition at which H product is equal to H reactant. If you try another temperature, if it came to your exam, I may help you to start with the temperature to start with. If you assume the temperature is 1800, still you will get negative value of H product. So still H product is less than H reactant. So I cannot interpolate in this case. We can extrapolate, but so let's assume 2000. You will find the H product minus H reactant. Sorry, this is H product. Okay, but the difference H product minus H reactant, in this case it will be still it is a negative value. This difference should equal to 0. But if I tried another case 2200, you will find the difference H product minus H reactant is a positive value in this case. So just we have one negative value H product minus H reactant and one positive value And the value in between should be actually when we have H product minus H reactant is equal to 0. Okay, so I will assume the temperature is 2200 and calculate H product. So here, let's say T product, I will assume 2200 degrees. I will calculate H product, and in this case I will calculate the difference H product minus H reactant. It will be a given value. This value should be a positive value. But at a temperature, let's say at 2000, if the temperature is 2000, you will find H product minus H reactant. This is a negative value. But we need to calculate the temperature, which is T adiabatic, we don't know, at which we should have the difference H product minus H reactant should equal to 0. Can we do interpolation, Shabab? So we can say T, let's say this is T product 1 and this is T product 2. And let's say H product minus H reactant, let's say this is delta H1. And this there, we will call it delta H2. This is something minor. We can say T adiabatic minus T product 1 divided by T product 2 minus T product 1. That should be the same. Delta H, at T adiabatic, we should have delta H is equal to 0 minus delta H1 divided by delta H2 minus delta H1. And by this interpolation, we can calculate the adiabatic flame temperature. In this case, can be calculated. Is that clear, Shabab? Is that clear?
Yeah.
So, Doctor, can we choose just a random low temperature and a random high, very high temperature?
Yeah, and the accuracy in this case of the interpolation will be low. But there is something else, Shabab. You can see here the number of moles of nitrogen are the dominant in this case. This is a big number of moles. That means the properties of nitrogen should dominate actually the properties of the combustion product. We can assume here, you will see here, you will have delta H in sulfur formation from the table. You can get those values from the table. Then it will result with some constant plus, let's say, some constant delta H CO2 plus some constant delta H H2O plus delta H O2 plus delta H N2. Okay? Then I can assume all product as N2. So all of this delta H, I will assume actually all of this are N2. Then I can get actually this H product as number plus a constant multiplied by delta H N2. And H product is equal to H reactant. Then I can get delta H N2. Go to the table for nitrogen, table A3, and they will get actually a temperature that corresponds to this delta H for N2. You can start with this assumption temperature. It should be around there. Okay. This is an assumption. Here is another example. You can see in this example, but here we have an insulated rigid 0.7 meter cube tank. What does it mean, Shabab? What does it mean, rigid tank?
Constant volume.
Exactly. So the case in this case, you have this constant volume, and in this case, the condition for the adiabatic flame temperature should be U product equal to U reactant in this case. He said insulated. Insulated, Shabab, means that the heat transfer is 0 and the combustor is adiabatic. And the constant volume, the volume is given. He said contains 0.05 kilogram of ethane, C2H4, of 100% theoretical air. This air is at 25 degrees C, and also the fuel is at 25 degrees C. The fuel is ignited and the complete combustion occurs as we use when we write down the combustion equation, and we need to calculate the final temperature, which is the temperature of the product, and also the final pressure. Final temperature, which is the adiabatic flame temperature. So it will be U product for constant volume combustion, adiabatic combustor, so U product will equal to U reactant in this case. So it will be the same, but we have to add R bar multiplied by, we have to subtract from the enthalpy R bar multiplied by delta H in this case. R bar multiplied by temperature. Okay. Type constant volume. Volume is equal to 0.7 meter cube. Constant volume rigid tank. That means the case is a constant volume. Combustion insulated. That means the heat transfer is equal to 0, and that means actually the temperature is the adiabatic flame temperature in this case. And the condition for this is U product is equal to U reactant in this case. Just to write down, he said we have 0.05 kilogram of ethane. He give us the mass. But to solve, we can just assume we have 1 kilomole of ethane, C2 actually H4, and then plus lambda, it is stoichiometric, plus gamma will equal to X plus Y over 4, it will be 3 O2 plus 3.76 N2, and then you can calculate the combustion product. And as we said, we can apply U product will equal to U reactant. We can calculate U reactant. We have the temperature, but we cannot calculate the enthalpy of the product in this case. Still, it is function of delta H, of other component, of all components. Then we'll do the assumption at temperature T1, we can go and we can calculate U product 1. And at temperature T2, we can calculate U product 2. Here, Shabab, if you calculate, you will find that the enthalpy of the reactant, let me check here. So here actually the right hand side for the enthalpy of the reactant, you can calculate actually this value. This value, what it should be equal to 157,900. So let's say this is your reactant. Because you have to look at this number when you assume 157,900. This is kilojoule per kilomole fluid. This is the internal energy of the reactant. Okay. Right, I will assume temperature T1, T product 1, and I will calculate actually U product 1. You will find here, let's say I will start with temperature equal to 2600. Okay. Because this is a stoichiometric combustion. So the temperature, if it is a stoichiometric combustion, we expect to have higher adiabatic flame temperature. So I will start with 2600. When you calculate the internal energy of product, you will find this value is equal to 136,500. Okay. So this number, Shabab, is less than what? Less than U reactant. So U product should be equal to U reactant. But when I assume this temperature 2600, I got U product which is less than the U reactant. That means I have to increase the temperature of the product. If you increase this temperature to 2800, you will find this number 149, and still this number will be less than U reactant. That means I have to add to increase the temperature, and then you can increase the temperature if it is 3000 Kelvin. In this case, then you will find this number U product 2 will equal to this value, which is 161,500, and this value is greater than U reactant in this case. Okay, that means the temperature that we are searching, which is the adiabatic flame temperature, should be in between, at which U product is equal to U reactant, is equal to this value. Okay, equal to this value. 157,300. Then you can do the interpolation. T adiabatic minus T1 over T2 minus T1 will equal to, this is, so T2, T adiabatic minus T product 1 divided by T product 2 minus T product 1. That should equal to, at T adiabatic, at this condition, when the temperature equal to the adiabatic flame temperature, U product should equal to U reactant. So U product, which is the same as U reactant, which is this value. Okay, minus U product 1, we have calculated at T product 1 divided by U product 2 minus U product 1 in this case. Okay, is it clear, Shabab? So either we can calculate U product, we can interpolate either with the difference H product minus H reactant, like this example. We did this interpolation this way using delta H, and at the adiabatic flame temperature, this delta H or delta U should be equal to 0. Or we can interpolate with the value of U product or H reactant itself. We say T adiabatic. At T adiabatic, U product should equal to U reactant in this case. Okay, minus U product 1 divided by U product 2 minus U product 1. Is that clear, يا شباب? Clear?
Yes.
I need to calculate also. The pressure. So usually the analysis, since the beginning, I told you we are following the ideal gas model. That we assume actually this is the combustion product and reactant are ideal gases, and that is not the case, but this is an assumption. So for the ideal gas model, we say BV is equal to MRT, and this M is equal to the number of moles multiplied by the molecular weight, and R is equal to the universal gas constant divided by the molecular weight, and this is the temperature. Molecular weight was molecular weight. That means we have BV should equal to number of moles multiplied by the universal gas constant multiplied by the temperature. I need to calculate the pressure of the product. So the pressure of the product multiplied by the volume of the product equal to the total number of moles of product. Universal gas constant is 83.14 multiplied by the temperature of the product, which we just calculated, which is the adiabatic flame temperature. But that should be substituted in Kelvin. And you are aware of that. Type, we have written down the combustion equation for 1 kilomole of the fuel. Plus, this is the combustion equation. But actually, he said in this problem that we have a tank, constant volume rigid tank. This volume is equal to 0.7 beta cube, and this is actually a rigid tank that contains 0.05 kilogram of the fuel. So this is the mass of the fuel. When I wrote down the combustion equation, I assumed we have 1 kilomole, but that is not representing the case. So if we have mass of the fuel is equal to 0.05 kilogram, that means the number of moles of the fuel should equal to this mass divided by the molecular weight of the fuel. Mass 0.05, molecular weight of the fuel, which is C2, will be 24 plus 4, it will be 28. So if you divide this, we calculate the actual number of moles of the fuel inside the tank. But we have written the combustion equation for 1 kilomole. Then just divide actually the whole equation by this number of moles of the fuel. So if we have this number of moles in the combustion equation, then in this case the number of components in the product will be different. We assumed we have 1 kilomole. For 1 kilomole, we should have in the product 2 CO2 plus 2 H2O plus, this is stoichiometric, we don't have O2, it should be plus 3 by 3.76 N2. So the total number of moles of product for 1 kilomole of the fuel, if you calculate this value, total number of moles of product will equal to about 18 point something. But this is for 1 kilomole of the fuel. But if we have the actual number of kilomole of the fuel is this value, then I can calculate the total number of moles of the product. I have to divide it actually by the number of moles of the fuel. Then we can calculate the number of moles of the product that correspond actually to those 0.05 kilogram of the fuel. Then we can get number of moles of product, substitute here. We have the adiabatic flame temperature, gas constant, volume is given, then I can calculate this pressure. In this case, this is calculated in kilojoule per kilomole, so this pressure يا شباب should be calculated in kilopascal. Okay? Is it okay, شباب? So Saeed? Saeed?
Yes, doctor.
Is it okay?
Yes.
Right, that's fine. Type.
So 18 divided by the number of moles.
18 divided by the number of moles of fuel.
To calculate the, okay.
So Shrab, we assume in the combustion equations that we have 1 kilomole of the fuel. But actually we don't have this 1 kilomole. We have only 0.05 kilomole.
Shouldn't we multiply the whole equation by the number that we got? I mean the
Yes.
number.
You have to multiply the whole equation by this number. So the number of mole of product will be reduced in this case.
Got it. Yes.
So just if you divide it, you will get the same value. Okay. The last topic I have to talk here is the efficiency of any combustion system. The efficiency of any combustion system or any heat engine in general, not only combustion system. So if we talk about internal combustion engine or gas turbine, or if we are talking about steam cycle power plant for electrical power generation, also we consider it as a heat engine. Heat engine, Shabab, we have defined from the first class, is any engine that is working on a cycle that can convert the heat into work. And in this case, for any heat engine or combustion system, any system that can convert heat into work, example of this is the internal combustion engine or gas turbine. That should equal to what we get the network output divided by the input, initial input. We call it the thermal efficiency. Okay, divided by the initial input, which is the fuel energy, the chemical energy of the fuel, which is function of the heating value or the calorific value of the fuel, and we have to multiply by the mass flow rate of the fuel. So mass flow rate of the fuel multiplied by the heating value, and that should be actually the power output or the rate of work done, which we call it work done. That should be calculated in kilowatt, heating value in kilojoule per kilogram fuel, and this is actually in kilogram per second, kilogram fuel per second. So kilogram with kilogram, it will be kilojoule per second, which is equivalent to kilowatt in this case. And we can calculate Shabab the power or work dot net from the first law of thermodynamics, Q dot minus work dot will equal to H dot product minus H dot reactant. We can just consider the rate form of the first law. Using this equation, we can, as we have done example last time on a gas turbine, we were able to apply this equation and calculate the net power output of this gas turbine. If we divide it by the mass flow rate of fuel by the heating value, then we can calculate the efficiency of this gas turbine. Also, this law, Shabab, as I told you, can be applied for any heat engine, any system that can convert the heat into work. Like a steam power plant. In a steam power plant, we have the pump that takes actually the water, pure water, raise this pressure of the water to the pressure of the boiler. So we have a boiler here. In this boiler, Shabab, this boiler, inside this boiler, we have a burner. This burner burn, heat is added here to the boiler through burning fuel. So we have here burner, we burn the fuel plus air, then we generate heat. This heat will be absorbed by the flowing water. The boiler is a kind of heat exchanger. We have water is passed inside the tube, and we have flame around, or the exhaust gases are around. Then this water, liquid water, will be just converted to steam under high pressure, under high temperature. Then we can take this steam and we can expand it inside the turbine. This is a steam turbine. Then we can generate shaft power in this case. In a steam turbine, this steam turbine is connected to an electric generator. Then we can generate electrical power. The steam leaving the turbine is under low pressure. So usually it is subcooled or saturated steam. Then we have to pass it, but still it is hot, Shabab. So we have to pass it through a condenser. Condenser is a cooling system in which we get actually cooling water. That's why steam power plant usually has to be close to a river or something, so that we can get cooling water, free cooling water. Cooling water will be coming in and it will absorb the heat. So we have heat is rejected here in the condenser. Then this water, which is still steam, we have some mixture of liquid plus vapor. Usually we have saturated mixture. Then it can be converted totally to liquid water, and then we can take this water inside the pump and then we can recirculate the cycle. In this case, Shabab, also the efficiency will equal to what? The final output, which is the shaft power network output, divided by the initial input to the cycle, to the boiler, which is burning fuel, the mass flow rate multiplied by the heating value of the fuel. And here is an example. He said we have in a certain unit of a steam power plant. Steam power plant, that means we have a steam cycle, gas turbine, a steam cycle turbine, not gas turbine. In this cycle, he said we have in the boiler, liquid fuel is used at a rate of 44,000. This is يعني شباب a real case example for a steam power plant. We have the fuel flow rate is 44,000 kilogram per hour of the fuel. The fuel has higher heating value of 42 megajoule per kilogram. It is 42 exactly 900 kilojoule per kilogram. So we have the mass flow rate of fuel. We have the heating value of fuel. So mass flow rate is given in this case 44,000 kilogram, and the heating value of the fuel is equal to 42,900 kilojoule per kilogram. And the net power output developed by this cycle is equal to 162 megawatt. So here, this power output, it is given 162 megawatt. So let's multiply by 10 to the power 3. Then we can convert it to kilowatt in this case. And mass flow rate of fuel, here this one is 44,000. This is kilogram per hour. Kilogram per hour, we have to convert it per second. So we have to divide by 3,600. And the heating value here is 42,900 kilojoule per kilogram fuel. It will be at the end this number multiplied by this number divided by mass flow rate of fuel divided by the heating value. Then you can calculate the thermal efficiency. Thermal efficiency يا شباب for steam power plant or electrical power generation, it should be around 30%. Okay, because actually a great portion of the heat actually is rejected inside the condenser. And this is a شباب heat rejected inside the condenser. Why we should use condenser يا شباب? Because we reject the heat here. And as you can see, the thermal efficiency of the cycle dropped down to 30%. Why we should use the condenser?
I think because of the pump, doctor. It's only calibrating liquids, water.
Pump cannot operate until we have, this is يعني one answer. And also شباب, this system is working on a cycle. For this system to continuously work and generate continuous shaft power, it has to work on a cycle. And the concept of operation of a cycle, you have starting from one point, do whatever processes you do, but you have to get back to the same initial point. So that we can repeat again. And then repeating the cycle again will generate continuous shaft power. If you don't get back to the same initial point, so you are not working on a cycle. You are just doing some processes and the system will stop. And this is related to the concept of operation. This is not related to the losses within the system, friction or heat. No, I have to reject this heat. I know I have this heat here, but I have to reject it. Because the system has to work on a cycle. I have to get back here to the same initial state. And this is related to the concept of operation. A simple example of this, let's say, the concept of operation of working on a cycle. Let's say I have here a piston cylinder device, and I have loads here. I take this load at this level, I add heat here, so that we have a gas. So when we add heat, the gas will expand, temperature will increase, pressure will increase, and that means we'll act with the pressure here, pressure force. This pressure force will raise the piston, and the load actually will be raised to this level. Then we can take this load. Now we did a job. We have raised this load from this level to this level. But I want to repeat this cycle. Yes, I have already added heat, and the piston has expanded here. And this heat, part of this heat used actually to move the piston, and still the gases, let's say the gas temperature has been raised actually to, let's say, 1000 degrees C. And after raising this piston, the gas temperature here is at 90 degrees C. But the piston is at the top. In order to repeat the cycle, what should we do? We have heat right now.
We need to lower the temperature.
We need to lower the temperature. And that means we have to reject the heat here. But don't say I have heat and I need to use it. So it's okay. If you want to keep this heat, just keep it. The piston will be up there and it will not get down. To repeat the cycle, we have to reject some heat. Then the piston, the gases will contract, and the piston will get back down. Then we can repeat it. So whenever you need to have something, you have to pay something. And this is related to the concept of operation. That is not related actually to the losses. This heat already in my hand, I have it, and I can use it. I have it, sorry, but I cannot use it. I have to reject it, so that I can repeat the cycle again, okay? And this is the concept of operation, Shabab, related to the cycle, the engine, the heat engine. Any heat engine to generate continuous work, it has to work on a cycle.
This
Yes,
is
Ali.
all the thermal efficiency, right? Not the overall efficiency, because we didn't consider the pump.
We didn't consider the electric generator.
Yes, yeah.
Yeah, this is not the overall one. This is the thermal efficiency of the cycle. Okay. طيب يا شباب, here يعني the schematic of thermal power plant. I think the guys you should be يعني aware of that. If you went to steam power plant for electrical power generation, it will look like this. We have here, this is the chimney, and here we have the boiler. The big part here is the boiler, in which we have the fire, steam. We are burning here exhaust gases. The gases are burned, so we generate hot exhaust gas. And here steam actually is just flowing inside those tubes, inside the boiler, in order water is converted from the liquid state to the steam state inside the boiler, inside those tubes, and the exhaust gases will be leaving until it reach out of this chimney. This here, Shabab, we have yani turbine. Usually we divide the expansion not only using one turbine. We use high pressure turbine, then intermediate pressure turbine, and then we have low pressure turbine. So the flow of steam comes into the high pressure turbine and leaves the turbine. We take it back to be heated back in the boiler, and then we get it back to the intermediate pressure. And then at the final state, we pass it through the low pressure turbine. All of these turbines are on the same shaft, and they are connected to electric power generator, and the electric power generator is connected actually to the electricity grid. Then we can have the electric power. For the condenser, as I told you, the condenser we use, for the condenser here, we just use cooling water to cool down the water that is flowing inside the circuit. This cooling water is coming usually, if we don't have a river, Shabab, or something, or if we have a problem with flooding water, then in this case, we can use a cooling water outside circuit. This cooling water will be heated by the heat of the steam. We can take this cooling water and then we can cool it down inside the cooling tower, and then we can get it back. And there is a pump actually to circulate. This is Shabab, the steam power plant for electric power generation. But usually, as I told you, Shabab, here the efficiency is about 30%. And that's why usually they combine, in any steam power plant right now, you will find there is a combination. They use a steam cycle plant, steam turbine, in addition to the gas turbine. So usually gas turbine is used in combine the cycle. Combine the cycles, that mean we have a steam turbine and the gas turbine. Usually, Shabab, if we have a steam turbine working, to run actually a steam turbine, shut it down and run it back, rerun the steam turbine again, usually it takes about 2-3 days of service until it gets back to the service. But in case of gas turbine, it can just immediately start, so that it is good to use the combination of gas turbine and the steam turbine. Usually we use the steam turbine in order to provide the basic load, and the fluctuating load that we may need it or may not need it can be provided through additional gas turbine. And also some gas turbine are used in providing the basic load. And now that the advances in the gas turbine, and here also in Saudi Arabia, as I told you, this is the world #1 actually country using, which has actually the biggest number of gas turbines that are in service. So all of these gas turbines are fed here by natural gas. And about 40% of the electrical power produced here in Saudi Arabia is produced by natural gas in gas turbine. Okay. Usually steam turbine and the boilers can use heavy fuel, dirty fuel in most of the cases. So usually boilers does not use natural gas. Natural gas, which is about 40% of the total power, is used in gas turbine. Here, Shabab, is what we call non-premixed gas turbine. Non-premixed, Shabab, this is the type of the flame. We call it non-premixed or diffusion flame. diffusion flame because it depends mainly actually of the diffusion of the gases of liquid plus of fuel plus air. In non-premixed means we have air is introduced in a separate stream to the combustor, separate from actually the flowing air. So usually fuel is fed from a central stream, and the air is actually supplied to the combustor from around this central stream, and they does not meet each other unless inside the combustion chamber. And that's why, shabab, there is a stoichiometric combustion zone. They are created actually in this kind of flame, and the combustion temperature in this case will be very high. Combustion temperature very high, that means we have dissociation of nitrogen, and that means we have higher emission of NOx in this case. If you look here, shabab, for the gas turbine, you will find less than 50% of the air is introduced for the combustion process. Most of the air actually is introduced around the combustor. Part of the air comes in the primary zone to complete the combustion. Another part is coming in a secondary zone to cool down the exhaust gases, and also the third part is coming in the tertiary zone in order actually to cool down the exhaust gases. So that when those gases are passed to the turbine blades, then actually they can match the turbine blade temperature, which should be around 900 to 950 degrees C. So we have to cool down the combustion. As you can see, shabab, we have calculated the adiabatic flame temperature. You can see it is around 2000, 2600, and in this case, but we have to use more air in gas turbine in order to cool down the exhaust gas temperature, in this case to a temperature around 1000 degrees Celsius, which can be actually withstood by the turbine blade. That's why, shabab, most of the current research in combustion, they are going toward actually the low temperature combustion. We call it pre-mixed combustion. Pre-mixed low temperature combustion. We call it dry low NOx because it will reduce the emission of NOx, because it will reduce the combustion temperature. In this case, instead of just feeding air and the fuel separately, and we have a stoichiometric combustion zone inside the combustor, that means the temperature will be very high. But what will happen if I just mix air and the fuel upstream and I use the excess air? So it is working very lean, and that's why in this case we call it lean pre-mixed. Lean, that means we are using excess air. So in this case I will mix the air plus the fuel upstream of the combustor. Then we can introduce them to the combustor with excess amount of air. That means in this case the combustion will result in lower temperature. So for the same combustor, shabab, same amount of fuel, in this case the non-premixed or diffusion flame combustor will result in temperature greater than 2500. But in case of pre-mixed, lean pre-mixed combustion or low temperature combustion, in this case we can reduce the temperature to 1800. And that should be less than the temperature at which dissociation of nitrogen occurs. And in this case, we can reduce the emission of NOx. And that's why we call it, shabab, dry low NOx. Dry low NOx, that means actually we are reducing the NOx emission, in this case. There is, shabab, also wet. This is dry low NOx. There is wet low NOx. Wet low NOx, in which we inject some fuel, some water vapor, inside the combustor in order to cool down the combustion product. And in this case, we cool down the temperature and we reduce the NOx emission. But in this case, this is a kind of wet analysis in which we just inject some water in order to reduce the temperature. But if you look here, shabab, for the conventional diffusion or non-premixed, we introduce about 30% of the air for the combustion, for the central combustion inside the combustion chamber, and about 70% of air is coming around the combustor in order to cool down the combustion product. But look here, in case of lean pre-mixed, low temperature combustion, we take about 60% of the air to inside the combustion chamber to perform the combustion process, and that should be excess air. So it will lower the combustion temperature in this case. And only we have 40% coming around the combustion chamber from the liner in order also to reduce the temperature, because as I told you, the temperature at the end should be around 1000 degrees C. So most of the current research يا شباب is toward the lean pre-mixed combustion or low temperature combustion in order to reduce the NOx emission. Okay, and this is also the current research running also in internal combustion engine. They try to use actually what's called the gasoline compression ignition engine, in which we can use the gasoline fuel in a diesel engine, but under very high compression ratio and under very lean condition. For gasoline engine, it should work near stoichiometric. Lambda should be very close to 1. It cannot go away from 1. But for this gasoline compression ignition engine, in which we use gasoline in a diesel engine, it works at higher compression ratio and at very lean condition. In this case, we provide much excess air. Lambda in this case can approach a value of 300% theoretical air, or even more, in order to lower the combustion temperature, and then we can lower the exhaust emission in this case. But usually, يا شباب, when we convert, if you went outside, you will find most of the gas turbines are conventional gas turbine, which are diffusion, which result in high temperature. Because the flame in this case, يا شباب, is very stable. Under part load, under full load, under any load, you will find this flame actually is highly stable due to the high temperature combustion. But in case of pre-mixed combustion, we pre-mix much air with fuel. So when it comes to the combustor, it will result actually in flame instabilities in this case. At lower equivalence ratio, the flame actually may blow out because we are using much amount of air and less amount of fuel, the flame will blow out. If I raise the equivalence ratio close to 1, in this case, upstream of the combustor, we have mixture of air plus fuel. That means this flame can propagate upstream of the combustor even, and it may result in explosion. We call it flashback of the flame. But in case of non-premixed, يا شباب, air is separated from fuel upstream, so the flame cannot go outside the burner. So usually pre-mixed flames are unstable, and we cannot operate يعني lean pre-mixed flame away from the rated power of the engine. So if we are using a gas turbine, lean pre-mixed gas turbine, so in this case the gas turbine should be working at its rated power or very close to the rated power. If you just went away from this rated power, in this case actually this flame will be highly unstable, and the flame and the gas turbine in this case may shut down in this case. Okay, that's why شباب we try to use a different burner design that can result in a stable flame for pre-mixed combustion, especially in gas turbine. We use a swirl stabilized combustor, micro mixer combustor. We have different designs, stagnation point, reverse flow combustor. We try to modify the inlet section of the burner in order to get actually a more stable flame. Then we can run this gas turbine under part load condition. There are different techniques, and also شباب to use Oxy Fuel Combustion technology is one of the carbon capture technology in which we burn using oxygen plus some recirculated carbon dioxide. So it is nitrogen free in this case. That means if we have a gas turbine adapting Oxy Fuel Combustion, that means in this case we should not have any NOx emission in this case, and the gas turbine should be NOx free. But also adding to lean pre-mixed combustion, if it is oxy combustion using carbon dioxide and oxygen, carbon dioxide have adverse effect actually on the combustion stability, and it will add actually to the instabilities that already exist in lean pre-mixed combustion, and the operability of gas turbine will be much limited in this case. شباب, there is a book. I will share with you this book. My book has already published with Springer Nature. I will assign each of you one group. Each group will be assigned one chapter. It is talking about about the clean combustion technologies in gas turbine. And we have tested already. We have a model gas turbine combustor in our lab, and we have tried actually different combustor design or burner design. And every time we get the flame stability map. You can just read about. It is very useful شباب to read it. This is for you. I can consider it as part of your thermo project. Each group will be assigned only one chapter. The book is 6 chapters. but I will consider only each group of you can consider 3 groups, each group 1 chapter. They can read it and they just actually give us a feedback what they have learned from this chapter regarding the clean combustion technologies for the gas turbine application. Okay, is it okay, Shabab? Do you agree on that? Sure.
Inshallah.
Yes,
طيب
Doctor.
I talk in the last 10 minutes too much, but I just was introducing to this. You can just, each group can take 1 chapter and then we can present it. Inshallah, I will send you the assignment maybe today or tomorrow. Then you may have 1 or 2 weeks to prepare this presentation. It will be very useful to read about this. This gas turbine, Shabab, this is schematic of industrial gas turbine. A gas turbine consists here of compressor. We call it the cold section. The compressor compresses the gases to the pressure of the combustion. Usually we have more than 1 combustion. We call this can combustor. We call it multi-can combustor because we have multiple combustor around the shaft, and then the combustion gases are passed through to expand through the turbine. Then we can generate the shaft power in this case. This is a cross section of a small gas turbine also for industrial application. This is how it looked like, Shabab, the gas turbine, the size of the gas turbine. But this gas turbine mainly is one of the biggest gas turbine in the world by GE. Largest gas turbine. This is the model of the gas by Siemens. Sorry, this is the model of the gas turbine, and you can imagine here, Shabab, the gas turbine can provide a power of 375 megawatt. Okay, 375 megawatt. Look at this example for a steam power plant. The power output was 162 megawatt. This is a steam turbine, and the steam turbine should be able to give more power. But you can see the advancement in gas turbine. Now we can have a gas turbine that can almost provide double of the power of a steam turbine. Okay, and that's why here we have here in Saudi Arabia and different countries, they are using the gas turbine for electrical power generation. Gas turbine also, Shabab, can be used in jet engines. But in jet engines, we use a small turbine. This small turbine is just used to provide the power for the compressor. But most of the gases will be left under high pressure, high temperature. So it will be expanding here in a nozzle. This is a nozzle. The area is reduced in the flow direction, so the velocity will be increased of the gases. Then, based on the second law of Newton, the force, a thrust force, will be generated in the reverse direction. This thrust force is equal to the rate of change of momentum in this case. Like, Shabab, if you have a balloon filled it with air, if you lift the balloon and we open, the balloon actually will be flying in the reverse, in the opposite direction at which the air is leaving. And this is the idea, Shabab, of jet engines, the engine used in aviation, in civil aviation and also military application. We have the exhaust gases are expanding inside a nozzle, then we can generate thrust power in this case. This is a turbofan engine. You can look at it. This is used actually in Boeing 757 aircraft. This is Rolls-Royce engine. In turbofan, Shabab, we call it turbofan engine. Usually they use in the aircraft, they use fan, which you see actually once you look at a jet engine, if you have tried a flight or something, when you look at the gas turbine engine, you will find the fan here. This part is the fan. This fan draws the air, takes actually more air to the engine. This air, actually part of it is used in the combustion process here, and most of the air is coming around the engine. For 2 reasons, in order to cool down the temperature of the engine, and also we get additional thrust of this air. And about 40% of the thrust, Shabab, and maybe 50% of the thrust of the jet engine is coming from actually the air that is not burning. Because this fan actually sucks more air, massive amount of air. It will be passing here in the outer, in the annular part, and it will be leaving with higher velocity, so it can generate additional thrust power, in addition to the thrust generated by the turbine itself. Okay? So that's all, Shabab, for today. Do you have a question, comment?
Doctor, why the air is leaking at higher
Sorry?
velocity?